So the name of the course is Introduction to Statistical and Probabilistic Methods, right? And this course has been divided into two parts. You know, that is the convention followed in our department. So I'll be covering the first part. These are the email IDs, my email IDs. So I'll be sending the meeting link from this particular Gmail ID. Okay. And
Ma'am, your screen is not visible.
oh, I forgot to share the screen. Sorry. Now, can you see the material?
Yes, ma'am.
Yes, ma'am.
Okay, so this is the name of the course, Introduction to Statistical and Probabilistic Methods. And these are my email IDs. Okay, a meeting links will be sent from this particular ID, and other communications will be done using either of these two email IDs. So as you know, the course has been divided into two parts. This is the entire syllabus. I'm not reading out the entire syllabus. The syllabus has been divided into two parts. The first part, part 1, will be covered by me, and I don't know, this time part 2 will be covered by, I don't know, who is the teacher for part 2, Professor Abhijit Mukherjee or Professor Subroto Pal? Hello?
Yes, ma'am. I'm checking once.
You have got the routine, no?
Yes, ma'am.
Ma'am, it's Subroto Pal.
Okay, fine. So the syllabus of part 1 is review of probability concepts, rules of probability, conditional probability, Bayes formula. Then we'll come to concept of random variables, probability distributions, moments of random variables, moment generating functions, discrete distributions, binomial Poisson, continuous distributions like uniform, exponential, Gaussian, log normal, etc. Then we'll discuss bivariate distribution or joint probability distributions. And after that, we'll directly come to the notion of random process, what is meant by random process. We'll discuss first and second order statistics, etc. What is called autocorrelation function, what is known by cross correlation function, all these things we'll discuss. These are a bit advanced topics. So this is the detailed syllabus for part 1, and up to this is basically a review part. Already you have studied, and you have studied these topics in the school level. So review of probability concepts, rules of probability, conditional probability, Bayes formula, all these things have been taught in the school level. So in the introduction, we'll just glance through this topic, and after that we'll start discussing what is meant by random variable. Now these are the reference books, some of the reference books. So for part 1, we'll have to refer to this book, Peebles by Peebles, and this is another very good book written by Papulis and Pillai. Now course outcomes. So you know there's an honors course, there's an honors course, and the course outcomes are at the end of the course, the students should be able to, the first course outcome is should be able to state probability concepts, rules of probability, conditional probability, the notion of random variables, Bernoulli's trial. Recall, the level is K1, basic level. This is basically the recapitulation part. You'll have to recollect all this topics. Bernoulli's trial also you have studied, right? Have you studied Bernoulli's trial?
No, ma'am.
Yes or no?
No, ma'am.
No, ma'am.
Human.
Okay. Now the second course outcome is the student should be able to describe various distributions, both continuous and discrete, operations performed on a single random variable and moment generating functions, and the essence of sampling theory. The sampling theory will be discussed in part 2. So the level is K2 understanding. Next course outcome is the student should be able to develop the knowledge on bivariate random variables, independence, correlation, estimation theory along with different estimators, percentage confidence level, regression analysis, etc. So from this portion onwards, these topics will be covered in part 2. The level is K3. That means applying. You'll have to apply your knowledge. The fourth course outcome is the student should be able to analyze the properties of random processes of different orders in the presence of noise and test statistical hypothesis. K4. So the random process of different orders will be discussed in this part, and hypothesis testing will be discussed in the second part. And the last course outcome is the student should be able to devise statistical analysis of measurement error and uncertainties and relate the outputs of LTI systems with random inputs. So this is quite a high level, K5. The level is K5, and the nature of this level is evaluating. That means given a problem independently, the problem might have multiple solutions. So independently, you'll have to solve the problem. You'll have to choose a particular answer. Now, chapter 1, this is basically the introductory chapter, fundamental concepts on probability theory, recapitulations. So let's start. Review of probability concepts. I'm reading a bit fast. If you find any difficulty, please inform me. The word probability literally denotes chance. Actually, the meaning of probability is chance. So the word probability literally denotes chance, and the theory of probability deals with the laws governing the chances of occurrence of phenomenon which are unpredictable in nature. That means we cannot predict the occurrence of a particular phenomenon with 100% guarantee. We cannot ensure the occurrence of that particular phenomenon. That's why the phenomenon is called a chance phenomenon. Now, historically, the probability theory originates from the games of chances played by tossing coins, throwing dice, etc. And its importance has enormously increased over the years. That is the history part. The theory of probability deals with averages of mass phenomenon occurring sequentially or simultaneously, like electron emissions. You will be able to relate this domain of application, electron emission, telephone calls. In the next 1 hour, how many calls are going to arrive at your mobile phone, right? So that you cannot predict, that you cannot say with 100% guarantee, okay, I'll receive exactly 5 calls. So that's why that is also a chance phenomenon. Radar detection, quality control, system failure. Suppose a device, an electronic device has operated for say 3 years. Now within next 3 years, exactly when the system is going to fail. If you want to ask this question and if you want to find the answer to this question, that falls under this category, system failure, when the system is going to fail. Games of chances, already we have discussed this. Games of chances means tossing of coin, throwing of dice, etc. Noise is absolutely a random phenomenon. We'll discuss noise in detail. Birth and death rates at this particular instant, at this time instant, how many newborn babies are taking birth, that we cannot say, exact, right? Or in the next 1 hour, how many babies are going to take birth, that cannot be predicted. Similarly, death rates cannot be predicted. Queuing theory is also a very interesting domain or application domain of probability theory. We form queue in many places, in a shopping mall, in a particular shop, or in petrol pump, right, to get the fuel. We form queues, that means waiting lines, right? Now, when we'll reach the service booth, when we'll reach the service person to get the service, why we form this queue, why we form this line? To get a particular service, right? So when we are going to get that particular service, that cannot be predicted clearly. Multiple queues can be formed. A person can break a queue and join another queue. This is a typical human behavior. Am I clear?
Yes, ma'am.
বোঝা যাচ্ছে কি বলছি?
Yes, ma'am.
So how a queuing system is going to behave, that falls under this particular topic, queuing theory, and this is a very interesting topic, I must say.
Ma'am, একটা question ছিল।
বলো।
Ma'am, you talked about noise. তো যখন noise বলছো, তো noise আর chaos এই দুটো কি একই জিনিস নাকি কিছু difference আছে?
না, completely different.
আচ্ছা, মানে different কি খুব মানে শর্টে বলতে পারেন কিরকম, মানে কি difference basically?
chaos এক্ষুনি ডিসকাস করব নাকি যখন নয়েজ ডিসকাস করব তখন একটু নোট করে রাখো, তখন বললে ভালো হয়, রিলেট করতে সুবিধা হবে।
ঠিক আছে ওকে।
একটু নোট করে রেখো, আমি chaos ডিসকাস করে দেবো।
ঠিক আছে ম্যাম, করে দিচ্ছি।
So it has been observed in this and other fields, certain averages approach a constant value as the number of observations increases. In case of chance experiment, what we do, we perform experiments repeatedly and we observe the result of the experiment, right? And we go on performing the experiment repeatedly, and finally we say that the result is reaching at a particular value, constant value, and often we define that constant value to be the average one. Okay, we expect a particular value. These things will be discussed in detail, just to begin with. So, and if we get such an average, such an expected value, then what will be the advantage? So for any subsequent experiment, when we'll perform the experiment once again, then from that average value, we'll be able to predict the output of the experiment, even without performing the experiment, right? So I'll come to this point once again. So consider a coin tossing experiment for which the percentage of heads approaches 0.5, that we assume 0.5, or it may be some other constant. So this is one constant value. Now, the purpose of this theory is to describe and predict such averages in terms of probabilities of events. Events you have studied. you know what is meant by event, though we'll glance through this very quickly. The probability of an event A is a number denoted by P within bracket A. That means probability of A assigned to this event. This number could be interpreted as if the experiment, that is the definition, if the experiment is performed n number of times and the event A, if we can define an event and if we denote that event by A, then if the event A occurs in A times, then with a high degree of certainty, we can say that the relative frequency Na by n, this is Na by n, of the occurrence of A is close to the probability of A. Okay, again I am repeating, this is the definition. To start with, if the experiment is performed n number of times and the event A occurs in A times, then with a high degree of certainty, the relative frequency Na by n of the occurrence of A is close to probability of A. So just go through this definition thoroughly, because some observation can be made from this particular definition. So we can write that probability of A is nearly equal to Na by n. Now, you see the definition is not a very concise one, a very precise one. The interpretation is a little bit imprecise. Why? Because these terms with high degree of certainty, close to, these are not very precise terms, and these terms do not have any clear meaning. That's why this definition is said to be an imprecise definition. However, this lack of precision cannot be avoided. Nevertheless, the theory is an exact discipline developed logically from clearly defined axioms, and when we apply this theory, that is probability theory, to real problems, we find that yes, probability theory really it works. So far, do you have any question?
No, ma'am.
Now, how to ascertain the probability of an event? For the time being, I'm assuming that we know what is meant by event or what is the definition of event. So now our objective is to find out what are the manners with the help of which we can ascertain, we can determine the probability of an event. So the application of probability to real problems, the following steps must be clearly distinguished. What are the methods? You see, observation. The first term is observation. The second term is deduction. The third term is prediction. Observation, deduction, prediction. So first we'll discuss the first term, observation. This is basically a physical means. So what we do, we determine by an inexact process the probabilities PAI of certain events AIs. Right? How? This process could be based on the relationship NAI by N, that is, could be based on that relative frequency concept. So could be based on the relationship Na by N between probability and the observation. I'm coming to the observation. The probabilistic data PAI equal the observed ratio Na by N. Okay, that means what we are doing, we are actually performing the experiment. That means, this is the first example, a die is rolled 1,000 times. And let's assume that after performing the experiment 1,000 times, the value of n is 1,000, the 5 shows 200 times. Then as per this definition, as per the previous definition, that is depending on the definition which relies upon the concept of relative frequency, probability of getting a 5 will be equal to 200 divided by 1000, which is equal to 0.2. So how did we get this value of the probability? That means probability of the event, which is equal to 5, the die will show 5, by actually performing the experiment and observing the result of each and every experiment. Am I clear? So that's why this kind of mechanism or this kind of technique is called ascertaining probability with the help of observation. And yes, we are physically performing the experiment, right? Now, also we can apply a little bit of reasoning, like we can assume that this chance experiment, throwing of a die, that means it's a chance experiment, right? So this chance experiment does have some properties of symmetry. Okay, so if we assume this, with the help of this assumption, we can conclude that if the die is fair, then because of this symmetry, probability of getting 5 should be equal to 1 by 6. So we observe the symmetry pattern of the chance experiment and we ascertain the probability to be equal to 1 by 6. So this value is different from this value. In this case, we have performed the experiment and we have observed each and every result, and therefrom we have determined the probability. So far, is this clear?
Yes, ma'am.
Yes.
The next one is deduction. Deduction. That means we'll not use observation, will not try to predict the value of the probability, but instead we'll try to deduce what is going to be the probability of an event. So it's basically a conceptual technique, not a physical one. So we assume that the probabilities satisfy certain axioms, and by deductive reasoning, we determine from the probabilities Pi of the events Ai, the probabilities Pbj of other events Bj. So with the help of reasoning, with the help of deductive reasoning, with the help of deduction, logical deduction, we'll try to find out, we'll start from a premise or we'll start from certain premises. I guess you understand what is meant by premise or premises. You know, in this particular context, what is the meaning of premise or premises?
Ma'am, could you repeat once again?
In this particular context, as I said, depending on certain premises, we'll try to deduce the probability of an event. So in this context, what is the meaning of premise or premises?
Other possible outcomes that can happen in this sense,
And
or
some
the
previous
factors
knowledge.
affecting this
What
particular.
is the meaning of premise or premises?
And some previous knowledge we have about the problem.
Exactly. So suppose hello. So I'm giving one example. I'm applying logic. So the logic could be like this statement: if A, then B. So what does it imply? If A is true, then B will occur or B will be true. Am I clear? So this if part is the premise. If part is the basis on which the conclusion is depending. Have you understood? Have you understood what I'm saying? Now, in case of deductive reasoning, what happens? The premises are always true. And from those premises, since the premises are always true, so from those premises, we conclude the then part, and the conclusion is always a certain one. No uncertainty is associated with the conclusion. In contrast, let's get back to this example. So a die is rolled 1,000 times and 5 shows 200 times. Then, so this is the premise in this particular example. This if part is the premise. Suppose there is a if. If a die is rolled 1,000 times and 5 shows 200 times, then P5 is equal to 0.2. Okay. Now, in this case, the premise is not true. The premise is not true all the times. It might so happen that the die is rolled 1,000 times and 5 shows, say, 500 times or 480 times. You get my point? So since the premise is not an absolute truth, hence the conclusion will change. The conclusion cannot be reached with 100% guarantee. So this kind of reasoning is called inductive reasoning. In this case, if the die is fair, the probability will be 1 by 6. So if the die is fair, if the die is not fair, then the conclusion will change, right? So the premise is not an absolute truth, and accordingly the conclusion may change. Have you understood what is the difference between inductive reasoning and deductive reasoning? Is it a little bit clear?
Yes, ma'am.
This is just for your understanding. So here you see, we are assuming that these premises are always true. That means probability of getting 1 is equal to 1 by 6, probability of 6 getting probability of this event, which is 6, is 1 by 6. Then probability that will get an even number will always be 3 by 6. It will not change. So that means from the knowledge of these probabilities, and we have considered we have considered this knowledge to be absolute truth, then from this knowledge we have derived the probability of another event, and the conclusion is always true, always fixed, always constant. Okay. The next one is, the third one is prediction. So have you understood what is observation and what is meant by deduction?
Yes, ma'am.
So the third step or third method could be prediction. We make physical prediction. That's why this term physical. We make physical prediction based on the numbers PBJ so obtained. So this step could rely on the equation. That means equation 1.1 means the equation which shows the relative frequency, Na by N, applied on reverse. If we perform the experiment n number of times, and if we find that an event B occurs NB number of times, then we can say that NB is nearly equal to, or will be very close to N into PB. That means We are predicting how many times this particular event is occurring. How? We know how many times the experiment has been performed, and we have assumed that this probability is known. So from this two information, or from this knowledge, we are trying to predict the number of times the event in B has occurred. So that is prediction. So for example, we roll a fair die 1,000 times. Our prediction is that even will show about 500 times. Why? Because we know that PB is given by 3 by 6, which is 0.5, N is 1,000, and hence even will show about 500 times. Clear? Have you understood this?
Yes, ma'am.
Yes.
Okay. So the step 1 and step 3 are based on inductive reasoning. So why? Because you see, we cannot answer these questions with 100% surety. Suppose, for example, that we wish to determine the probability of heads of a given coin. Should we toss the coin 100 times or 1,000 times? If you toss the coin 1,000 times and the average number of heads equal to 0.48, what kind of prediction can we make on the basis of this observation? Can we deduce that at the next 1,000 tosses, the number of heads will be exactly 480? So we won't be able to answer these questions clearly. So such questions can only be answered inductively. We cannot deduce the result in a clear-cut manner, in an unambiguous manner. So to conclude, we repeat that probability of an event A will be interpreted as a number, simply a number, assigned to this event. So probability of event A, suppose the value is 0.5. Suppose we have got the value either through observation or through prediction or through deduction, whatever. Let's assume that the value is 0.5. So it's basically a number associated with this event A. So repeat that probability of an event A will be interpreted as a number assigned to this event as mass is assigned to a body or resistance to a resistor. What is the value of the resistance of a resistor? Say the answer is 25 ohm. That means we are assigning a value, we are assigning a number with the resistor, and in this case, in case of probability, we'll assign a number with this event. So what is the logic behind this? A resistor is commonly viewed as a two-terminal device whose voltage is proportional to current, that we know. So resistance is V by I. Now, there are certain assumptions that we make. Often we don't explicitly mention this assumption these assumptions. Instead, we just associate a value of resistance with a resistor. What are the assumptions? So this representation is, or this equation is only a convenient abstraction. No, I'm not going into the detail of the concept of abstraction. For the time being, just assume that abstraction is a kind of representation. Okay, so the value of the resistor is being represented with the help of this equation. So this is a kind of representation. That's why we call it a convenient abstraction. Now, a real resistor is a complex device that with distributed inductance and having no clearly specified terminals. A relationship given by the above equation can therefore be claimed only within certain areas. in certain frequency ranges and with a variety of other qualifications, right? So also other qualification means if I assign a value to a resistor, I'll have to assume that the temperature is not changing, so on and so forth. So many assumptions are there. So that means the value which is associated with the resistor, that is not a very precise one, isn't it? So nevertheless, in the development of circuit theory, we ignore all these uncertainties. The value of the resistance is full of uncertainties, but when we solve circuits, then we ignore all these uncertainties. We assume that the resistance R is a precise number satisfying this particular equation, and we develop a theory based on it, that means circuit theory, and based on it and on Kirchhoff's law. So it would not be wise at each stage of the development of the theory we should be concerned with the true meaning of resistance. No, then what will happen? We'll not be able to proceed. Okay, we'll get stuck. So have you understood what I'm saying?
Yes, sir.
Now, these things are known to you. The theory of probability, random experiment. When a coin is tossed, either head or tail appears, but the result of any toss cannot be predicted in advance and is said to depend on chance. So that is the case with a die. I'm going a little bit fast. Do you have any problem?
No,
No, ma'am.
The word experiment is used to describe an act which can be repeated under some given conditions. Okay. So the conditions or the ambience should remain same, identical, and if we can repeat that particular act, then we'll call that those are the experiment. So random experiments are those experiments whose results depend on chance. The word random may be taken as equivalent to depending on chance. So these are some examples of random experiment. Tossing of a coin, tossing of a die, drawing cards, drawing balls from urn, studying the distribution of boys and girls in a family, so on and so forth. What is an outcome? The result of a random experiment will be called an outcome. The possible outcomes of a random experiment may often be described in several ways. So I'm giving one example since you know all these things. So in the random experiment of throwing 6 faced die and observing the number of points that appear, the possible outcomes are 1, 2, 3, 4, 5, and 6. Again, the outcomes could be defined like this: odd number of points, even number of points. So in the random experiment of 2 tosses of a coin, we know head, 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 tail, tail, head, tail, tail. Another example is given. Just look at this example. I'm not going to explain this. There are 36 possible outcomes in the random experiment of single throw of 2 dice, isn't it? What is an event? In the theory of probability, the term event is used to denote any phenomenon which occurs in a random experiment. So in effect, one or more outcomes are said to constitute an event. Events may be elementary or composite. An event is said to be elementary if it cannot be decomposed into simpler events. A composite event is an aggregate of several elementary events. Just a moment. So outcome and event may appear to have been used in almost the same sense, though it's not true. There is a subtle difference between these two. So as an outcome can be an event, and multiple outcomes can constitute an event. So outcomes are generally thought of as the ultimate results of a random experiment which cannot be split up further. That means outcomes are elementary events. Hence, these are sometimes referred to as elementary outcomes or elementary events. Any event or phenomenon connected with a random experiment is then defined as an aggregate or set in the mathematical sense of certain specified outcomes. In particular, a set containing only a single outcome is called an elementary event. Like even number will occur. That means it is a composite event, and we can split that event into 3 outcomes. That means either 2 will appear, or 4 will appear, or 6 will appear. Okay, I guess I don't have to repeat this. I guess you know what is the definition of outcome and what is the association between an outcome and an event.
Yes, ma'am.
Okay. Mutually exclusive, you know that. Events are said to be mutually exclusive when 2 or more of them cannot occur simultaneously. So mutually exclusive events can always be connected by the words either or. Events A, B, C, D are mutually exclusive only if either A or B or C or D can occur. Either A and B cannot occur simultaneously. Just go through this material, I guess you won't find any difficulty in understanding. Exhaustive, yes, that also you know. Several events are said to form an exhaustive set if at least one of them necessarily must occur. The complete group of all possible elementary events of a random experiment gives an exhaustive set of events. Right? So A denotes the event or number of points 1, 3, 5. B denotes the event at least 2 points 2, 3, 4, 5, 6. These 2 events together will give us an exhaustive set of outcomes or events. Now note that we have defined event A to be odd number of points, event B to be at least 2 points. So 2, 3, 4, 5, 6. So 5 is common, 3 is common. Okay. So these 2 events constitute an exhaustive set, but event A and event B are not mutually exclusive. Trial. Any particular performance of the random experiment is called a trial. Right? We can perform the experiment 1,000 times, and each experiment will be called to be a trial. Cases favorable to an event. Among all the possible outcomes of a random experiment, those cases which entail occurrence of an event A are called cases favorable to A. Is it okay?
Yes, ma'am.
Another term you are quite familiar with, equally likely. The outcomes of a random experiment are said to be equally likely if, after taking into consideration all relevant evidence, none of them can be expected in preference to another. So in coin tossing experiment, we cannot say if the coin is a fair one, unbiased one, then we cannot say that probability of getting tail will certainly be greater than the probability of getting head. No, we cannot give preference specific preference to any of these two events. That is, the first event is getting tail and the second event is getting head, or vice versa. So in coin tossing, as I said, two outcomes and they are equally likely. However, if two unbiased coins are thrown, the elementary events head, 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 tail, tail are equally likely, but the outcomes two heads, one head, no heads are not equally likely. I guess I don't have to explain this. So next one is classical or a priori definition of probability. A priori definition. This is the term we use. If a random experiment has n possible outcomes which are mutually exclusive, exhaustive, and equally likely, and m of these are favorable to an event A, then the probability of the event is defined as the ratio m by n, or with the help of symbols, we can represent that probability of A is equal to m by n. So that means, given a chance experiment, why do we use this term a priori? Given a chance experiment, if we can identify all possible outcomes which are mutually exclusive, exhaustive, and equally likely, right, then very easily we can identify number of cases favorable to an event, say A, and from that we can ascertain, we can determine the probability of that particular event A, like coin tossing case. So in coin tossing case, we know that single coin, so the outcomes will be either head and or tail. These two are mutually exclusive and these two events are equally likely. These two together constitute an exhaustive set, and hence we can say that the probability of getting head will be equal to 0.5 and probability of getting tail will be 0.5. We are not giving any preference to any of these two events, right? So since we know the probability, we know from this outcomes from this knowledge that the events are equally likely, exhaustive, etc., etc., we can determine the probability even without performing the experiment. So even before performing the experiment, we can say that if we toss a fair coin, then the probability of getting a head or getting a tail will be equal to 0.5. Again, I repeat, before performing the experiment. Before performing the experiment, we can say that the probability of getting head or tail will be equal to 0.5, right? So that's why this definition is called a priori. That means we can ascertain, we do ascertain the probability of an event before, a priori, before performing the experiment. So it's clear why we call this a priori definition of probability.
Yes, ma'am.
So it may be noted that probability as defined above is only a ratio of two numbers, in which the numerator m is the number of favorable cases and the denominator n is the total number of possible outcomes satisfying certain conditions. Those are the conditions. That means the events should be equally likely, mutually exclusive, exhaustive, etc. Therefore, the calculation of probability, the following steps should be followed. Enumerate, as I said, enumerate all the possible outcomes of the experiment such that they satisfy the three criteria of being mutually exclusive, exhaustive, and equally likely. count the number n of such outcomes. That is step 1. That means, you see, we are not actually performing the experiment. Okay, only we are trying to identify the number of outcomes abiding certain conditions, etc., for a given chance experiment. Now check how many of these cases are favorable to the event for which the probability is measured. Let this number be m. So by dividing m by n, we get the probability, and we know that the probability, the value of the probability, that means that particular number will lie within this range. The probability could be greater than 0, greater than or equal to 0, and less than equal to 1, right? So that's why this definition gives us an a priori definition of probability. Now this is a classical definition. Now there are some defects in classical definition. So what are the defects? Let's see. So the classical definition is based on the feasibility of subdividing the possible outcomes of the experiment into mutually exclusive, exhaustive, and equally likely cases. Unless this can be done, the formula is inapplicable. Recall, the formula is m by n, and n is the number of outcomes which are mutually exclusive, exhaustive, and equally likely. It might so happen that for a certain chance experiment, it will be difficult to find out possible number of outcomes, total number of outcomes which are mutually exclusive and exhaustive and equally likely. So in that case, we'll not be able to apply this particular definition. The phrase equally likely appearing in the classical definition is synonymous with equally probable, isn't it? Equally likely means equally probable. That means when we are trying to define the term probability, in the definition itself, we are using a term which is probable. That cannot be done, right? So in that case, the definition cannot be understood, clearly understood. You get the point? Suppose you are trying to define inertia. So in the definition itself, while you are trying to define inertia, then in the definition itself, if you use the term inertia, then will the definition be clear? And will your friend will be able to understand what is the definition of inertia? Because in the definition itself, within the definition, we are using the term inertia. So when we define a particular term, we cannot use that particular term in the definition. It is known to you, isn't it?
Yes, ma'am.
So here you see, while we are trying to define probability, we are actually using a term equally probable. So the definition is not clear. Now, the third problem is the definition has only limited applications in coin tossing, die throwing, and similar games of chance. Using this definition, we cannot, for example, find the probability that an Indian aged 25 will die before reaching the age of 50, because in this case we'll not be able to find out the outcomes. So such probability is required to be calculated for fixing premium rates and life insurance. So if you go by the classical definition, then this kind of probabilities cannot be computed. So we need some other means. Thus, it may not be practically possible to enumerate all the outcomes of the random experiment, and in that case, we won't be able to find out the probability of such an event. The definition fails when the number of possible outcomes is infinitely large. N will be infinity, will tend to infinity, and the probability will B is 0, which may not reflect the actual case. Sample space, sample points, the set of all possible outcomes of a given random experiment is called a sample space. Any particular outcome that is an element of sample space is called a sample point. The sample space is not a geometrical space. The sample space, within the sample space, certain points are there. Outcomes, it's basically a set of all the outcomes of a chance experiment. So it's not a geometrical space like state space or signal space. State space is really a geometrical space, right? But sample space is not a geometrical space. Clear?
Yes.
It is a universal set of outcomes. Often sample space of a random experiment can be given in several ways, but there is usually one which provides maximum information. So 3 tuples, when a coin is tossed 3 times or 3 coins are tossed simultaneously, the sample space contains 8 sample points and we get 3 tuples, head, 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 tail, so on and so forth. An event is a set of outcomes of a random experiment. In other words, event is subset of the sample space. So events may be elementary or composite. We have discussed this. A composite event contains more than one sample point. Sub-event, if A is subset of B, where A and B are the events of sample space defined on the sample space, then A is called a subset of event B. So this is an event, this is the definition of event A. Odd number appears, event B, even number appears, event C, 6 appears. So this event C, is subset of event B. And these two are composite events, and this is one elementary event. So events described by set operations, A and B are two events defined on the same sample space. So A union B denotes the event at least one of A or B. That is either A or B or both. This can be represented as A plus B. A union B is represented by A plus B. Intersection B denotes the event A as well as B. That means both A and B. And this is written as AB and it's called compound event. You have studied all these things, no?
Yes, sir.
So this is the complementary event, A bar, complementary event. A minus B denotes the event A but not B. That is both A and not B. So this can be represented with the help of this set theoretic notation, A union B complement. Mutually exclusive events, two events A and B are said to be mutually exclusive or disjoint if A intersection B is equal to a null set. So tossing of a die, this is the sample space, all these the outcomes or elementary events. 1 appears, 2 appears, 3 appears, 4 appears, so on and so forth. A even that an odd number appears, B event B that an even number appears, C 5 and 6 even that more than 4 appears, then A union C, you know it's going to be A 3, 5 and 6. B intersection C is only 6. Complementary event S minus A, that means even that odd number doesn't appear. A intersection B, A and B was odd number and even number, right? So A intersection B mutually exclusive, and hence it will give us a null set. So that means this is impossible. Even that an odd number as well as an even number appears, which is an impossibility. এগুলো কি আমার বলতে হবে?
No, ma'am.
Commutative law, distributive law, you know all these things. T. Morgan's law, duality principles, etc. So these are the three basic axioms of probability. Axioms of probability, three basic axioms of probability. The first axiom is, for every event A defined on some sample space, probability of that event should be greater than or equal to 0. Axiom 2, for the sure event S, probability of S is equal to 1. And for any finite number or countably infinite number of mutually exclusive events A1, A2, AN defined on a sample space S, probability A1 union A2 union AN will be given by probability of A1 plus probability of A2 plus probability of AN. And this can be represented with the help of this equation as well. For two mutually exclusive events A and B, probability A union B is equal to probability A plus probability B. Bayes' theorem, just ignore this part, given in the handwritten note, ignore this part. Bayes' theorem you have studied. Theory of total probability, I guess that also you have studied, isn't it? So if two events A and B are mutually exclusive, then the probability of occurrence of either A or B is given by the sum of their probabilities. That is, probability of A or B is equal to probability of A plus probability of B, or probability A plus B is equal to probability A plus probability B. This is known as addition theorem. So deductions from theorem of total probability: if all these events are mutually exclusive, then the probability of occurrence can be found from this expression. Probability A1 plus A2 plus AK will be equal to probability A1 plus probability A2 plus just generalization of this one, this equation. This is the complementary event. Probability of A bar is equal to 1 minus probability A, or probability A is equal to 1 minus probability A bar. Compound probability. The probability of occurrence of the event A as well as B is given by the product of unconditional probability of A and the conditional probability of B, assuming that A has already occurred. That means probability AB is equal to probability A into probability B, given that event A has occurred. So this is known as multiplication theorem. So mathematical expectation, we'll discuss expectation and variance in detail in the next chapter. So for the time being, in this manner, we find out the expectation. Now, whenever we'll try to explain what is meant by expectation or what is meant by standard deviation or variance, look, the mathematical expectation is the sum of the products of the different possible values of the variable. Which variable? So we'll have to learn, we'll have to study what is meant by the variable. That means we're talking about random variable. I guess you have heard the term random variable. So unless we understand the concept of a random variable, we'll not be able to understand what is meant by expectation and what is meant by variance or standard deviation, right? So in the next chapter, we'll start from this particular point and we'll start discussing the notion of random variable. So the issue which is most important for assigning values of probability for each and every event calls for the mathematical idealization, and that mathematical idealization is known as random variable. So far, do you have any question?
No, ma'am.
Okay. Now, I guess you know that noise is associated with an adjective which is random. Noise is completely a random phenomenon, though till now we don't know what is meant by a random process, but I guess this much you know, that noise is a completely random kind of signal. We cannot predict the actual nature of the noise, isn't it?
That's right.
So noise is random. So what is chaos? Just a moment. Should I close this file? Can I close this file?
Yes, ma'am.
Yes, ma'am.
Just a moment. Can you see the material?
Yes, ma'am.
Chaos is a typical behavior exhibited by some nonlinear element. Apparently, it appears that chaos is also a very random kind of thing, like a noise, though it's not actually true. You find out the diagram. Chaos. Should I stop the recording? Or should I record this part?
No, ma'am, it's okay if it is recorded.
Okay. So chaos, we know that we have studied linear time invariant systems, and we know that if the initial condition for an autonomous linear system, that means unforced linear system, right, where there is no input to the linear system, no forcing function, the dynamics of the linear system is actually influenced by the initial conditions only. So in that case, we know that for a stable linear system, if we slightly change the initial conditions, the stability of the linear system will not change. The system will remain stable. Do you agree? Do you
Yes,
agree?
Yes, ma'am.
আগের সেমিস্টারে লিনিয়ার কন্ট্রোল পড়েছো। Now that is not the case for non-linear system. So non-linear system can display a phenomenon called chaos, by which we mean that the system output is extremely sensitive to initial conditions. So for linear system, we have observed that if we change the initial conditions, the stability of the linear system will not change. But in case of a nonlinear system, certain kind of nonlinear system, certain type of nonlinear system, if we even slightly change the initial conditions, again we are considering that the nonlinear system is also an autonomous nonlinear system. That means there is no forcing function, there is no external input. So again, the dynamics of the nonlinear system is influenced by the initial conditions only. Now, if we even slightly change the initial condition, very slightly change the initial conditions, the output of the system gets completely different from the previous case. Suppose the first initial condition was, say, x10, first initial condition where x10 is a column vector, and the second initial condition which is slightly different from this initial condition x10, and let's denote it by x20, say, right? So for x10 the system will exhibit certain output, right? But for x20, though it's slightly different from x10, the output of the system will be completely changed, and the output cannot be predicted. For which initial condition, what is going to be the output of the nonlinear system, that cannot be predicted with 100% surety. So the essential feature of chaos is unpredictability of the system output. But no randomness is associated with the system, right? The model is quite precise. Even if you have an exact model of nonlinear system and an extremely accurate computer, that means there is no uncertainty. There is no input uncertainty, right? But the system's response in the long run still cannot be well predicted. So chaos must be distinguished from random motion. Why? Because in random motion, the system model or the input contains uncertainty. Clear? Either the system model is not a precise one, there is some model uncertainty, or that the parameters of the system are not defined clearly. That means there are some parametric uncertainty, or the input to the system is itself random in nature, right? So obviously the output of the system will be random, and the system will be said to be a random one. But in case of chaos, the model is an exact model, no uncertainty is there, only we are changing the initial condition slightly, but the system output gets drastically changed. So again, I'm repeating, chaos must be distinguished from random motion. In random motion, the system model or input contains uncertainty, and as a result, the time variation of the output cannot be predicted exactly. Only statistical measures are available. In chaotic motion, on the other hand, the involved problem is absolutely deterministic. there is little uncertainty. That means there is no uncertainty in the system model input or initial conditions, but the output is absolutely chaotic. So this is one example of a nonlinear system. So I guess you'll be able to at least relate this particular differential equation. The system which is being governed by this nonlinear differential equation is a mass spring damper system, isn't it? Do you agree? X double dot plus kx dot plus some fx, where fx is x to the power 5. So this equation represents a mass spring damper system or a nonlinear RLC circuit. Do you agree?
Yes.
Can you relate this equation?
Yes.
And here you see the system has been excited with sinusoidal input. So from this coefficient, you see the coefficient, the damping, the coefficient of the damper is 0.1. So it's a very lightly damped system. And why it's a nonlinear system? Because x to the power 5, presence of this term, x to the power 5 makes the system a nonlinear one. Had it been simply x, then it would have been a linear system. So suppose we consider two initial conditions. The first one is x02, it's a second order system. So we'll have two states. One is x0, one is x. The second state is dx dt, or x is x1 and x2 will be x1 dot or dx dt. So the initial conditions are like, the first initial condition is x0 is 2 at time t equal to 0, 2, and x dot 0 is equal to 3. And the second set is x at time t equal to 0 is 2.01. You see, this one was 2 and this is only 2.01. And this is 3 and the second one is 3.01. So we are changing the initial conditions only slightly, very, very slightly. The deviation is very, very small. But if you look at the output response, this is the response. This is xt versus t. Now, at time t equal to 0, the system start describing motion from this particular initial condition, which is either 2 and 3 or 2.1 and 3.1. Up to this point, you see the output of the system is almost same for both the initial conditions. Now, after this time instant, exactly we cannot say which one is going to be the time instant from where the outputs will start deviating from each other. Now you see there is a deviation. One output is shown with the help of thick line, the second output is shown with the help of this thin line, and you see after a while, okay, now in this region, fine, the outputs are quite close to each other, but after a while you see the outputs are completely different. So under such situation, we say that the system is exhibiting a chaotic behavior. Though there was no uncertainty associated, you see the initial conditions are precisely defined. So no uncertainty associated, no randomness in the input to the system, no uncertainty associated with the model of the system. Only we are changing the initial conditions slightly, only slightly, but the system breaks into a chaotic motion. কিছু বোঝা গেল?
Yes, ma'am.
Do you have any question? Do you have any question?
No.
No.
So I'm closing this file.
Yes, ma'am.